Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 8, 2026, just 2 days ago. It introduces a scalable framework and a massive dataset for predicting 3D object trajectories, achieving an average displacement error of just 0.019, which is a massive improvement over the 0.06 error rate of previous autoregressive baselines. The paper is titled ObjectForesight, Predicting Future 3D Object Trajectories from Human Videos. And as we'll see later, the fact that it outperforms commercial video generators like Luma AI Ray 3 suggests that explicit 3D reasoning is key for understanding physical dynamics. So Figure 1 illustrates the high-level workflow of this framework. It begins with an input video context, effectively observing a short clip of past motion to understand the scene. Next, the system performs a 3D estimation step, calculating the object shape and initial pose relative to the camera. Finally, it generates a future 6D prediction, projecting the object's trajectory in 3D space over time, rather than simply predicting future pixels. Well, while Figure 1 sketched the inference setup, Figure 2 details the automated pipeline used to curate training data. On the far left, the system ingests RGB clips from the Epic Kitchens dataset. Inside the central dashed box, it applies a sequence of vision models, first using Ego HOS for coarse detection, then refining masks with SAM2. This allows the system to reconstruct a 3D mesh using Trellis, shown in the top right of the panel. Finally, on the right, the pipeline outputs precise 6D pose estimations, tracking the object's translation and rotation. So, having curated the data, Figure 3 presents the core model architecture. On the left, the system takes a scene point map from the last observation and a normalized object bounding box, feeding them into a point transformer V3 encoder. This component creates a geometry-aware embedding, which moves to the center, where a diffusion transformer processes it alongside a history of clean past poses and noisy future tokens. Ultimately, the model predicts the noise to generate the smooth, denoised 6DOF poses shown on the right. Alright, with the model defined, Figure 4 now validates its performance by comparing real trajectories against the generated ones. The top row establishes the ground truth, visualizing future motion by overlaying 8 consecutive poses onto the last scene frame. In the bottom row, we see the predictions from ObjectForesight. The alignment is striking. The model accurately anticipates complex dynamics, such as the rotation of the plate in the first column, effectively mirroring the physical reality. So, while Figure 4 verified accuracy against ground truth, Figure 5 compares the method against a state-of-the-art video generator, Luma AI Ray 3. On the left, we see the shared context frames used to prompt both systems. The top row shows the output from ObjectForesight, which generates stable, temporally consistent 3D object poses directly. In contrast, the bottom row displays the results from Ray 3, where poses are extracted post-hoc from generated video pixels, leading to less consistent physical trajectories. Well, having seen the qualitative results, Table 2 now reveals the sheer scale of the data that powers this performance. The pipeline starts at the top, with over 76,000 raw video segments. Through the automated stages involving SAM2 and Trellis, the system extracts hundreds of thousands of tracks before rigorously filtering them. This culminates in the bottom count, yielding over 2 million high-quality 3D trajectories to train the model effectively. Okay, while the previous table established the dataset size, Table 1 reports the actual forecasting accuracy across 2 benchmarks. The top section focuses on the Epic Kitchens dataset, where the diffusion-based ObjectForesight DIT achieves an average displacement error of 0.019, beating the autoregressive baseline significantly. Moving to the middle section, the comparison against Luma AI Ray 3 is even more stark. The diffusion model maintains low error rates, whereas the video generator lags behind with an error of 0.084, proving that explicit 3D modeling works better than pixel synthesis. Wrapping up, 2 takeaways stand out. First, leveraging massive amounts of passive human video data allows models to learn genuine physical dynamics without robotic intervention. Second, explicit 3D modeling significantly outperforms pixel-based video generation for accurate trajectory forecasting. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.